Dr. Sridhar, back to you with another video session on transformer and loads. In our previous videos, we have discussed about transformer and no load and its associated phasor diagrams and whatever the performance equations of the transformer under no load conditions. And we also discussed about the EMF equations and other construction details and principle of operation. So in today's video session, we are going to talk about various phasor diagrams with respect to various loading conditions on transformer and load, and what is the formula used to calculate efficiency. These are the points majorly we are going to discuss in today's video session. So transformer and load is the secondary of the transformer is connected to the load. As we know that the primary is meant for the source voltage, supply voltage. Secondary winding is nothing but across which we are going to connect the load. The load can be different types of loads, that is nothing but it can be resistive or inductive or capacitive. Sometimes people will say that load is unity power, UPF load. UPF load is nothing but the resistive load, and lagging power factor load, lagging type load means nothing but the inductive, and leading power factor types of load is nothing but the capacitive loads. So don't worry about the represent types of loads. Loads can be with respect to passive nature, loads can be represented as resistive, inductive and the capacitance, or else based on the power factor also loads can be classified into unity power factor, inductive and capacitive. It means inductive is nothing but the lagging power factor, capacitive is nothing but it is a leading power factor. The current I2 flows through the secondary winding of the transformer, which is nothing but it is proportional to the how much of load we have connected to the secondary winding. Proportionally, there will be a current, it will be drawn from the secondary winding, that is nothing but that secondary induced EMF E2 will supply the required amount of current to drive the external load which is connected across the secondary winding. That is the scenario what happens. So what could be the current means? That current generally it is represented as the I2. The magnitude of the secondary current depends on the terminal voltage and the load impedance. Yes. So the phase angle between the secondary current and the voltage depends on the nature of the load. Because just now also we have discussed types of the loads. If it is a resistive load, the secondary voltage and that secondary voltage means V2 and the secondary current, that is I2 current, it will be in phase. So for the resistive load it happens. Otherwise it will be the lagging. For inductive loads, it will be leading for the capacitive types of load. The operation of the transformer on load condition, it can be explained as below. So when the secondary of the transformer is kept open, suppose if the transformer is initially, what happens? Let us assume there is no load. Now under no load conditions, what will be the current supplied by the primary and what will be the flux that will be there in the magnetic circuit and what will be the secondary current? And similarly, the same behavior of the transformer if some load is connected and how the transformer it will behave with respect to the different loading conditions. Like how we are going to proceed, and that is a procedure to analyze the behavior of the transformer under loading conditions. So that's why let us take first the transformer under no load conditions. When the secondary of the transformer is kept open, it draws the no load current from the main supply. So in the primary loop, only we will get the no load current. The no load current, whenever it passes through the primary winding, it sets up a magnetic motive force N0, N1 into I0. So N1 is nothing but the number of turns, I0 is nothing but the no load input current. It will be there in the primary winding. So N1 into I0, and this force sets up some magnetic flux. Generally this magnetic flux under no load only we are going to consider. So this magnetic flux can be represented as pi naught. So this current flux is nothing but the pi naught, and this is nothing but the N1 into I naught is the MMF. So finally what happens? Once the load is disconnected from the secondary winding, now if the supply voltage turned on, then it sets up some no load current. That no load current is nothing but I naught is the no load current. This no load current will drive some amount of flux from the primary winding to the secondary winding through the magnetic core. So that flux is nothing but the pi naught is nothing but that is the flux. So this pi naught is nothing but flux under no load conditions. So next one is when the load is connected. Suppose here if you could see if the load is connected. Once this load is connected, immediately this I2 will be established because of the induced EMF in the secondary winding, that is E2. So I2 current flows through the secondary winding. The secondary current induces the magnetomotive force. So this I2, whenever it is established, then whenever this I2 current flows through the secondary winding, now there will be a magnetomotive force. This many number of ampere turns will be there in the MMF of the secondary winding. So this N2I2, is nothing but, already we have discussed, this N2I2 is nothing but the magnetomotive force in the secondary winding. This will also proportionally drives its own flux, that is nothing but the flux that is nothing but the pi 2. Why we are representing pi 2 means this pi 2 is nothing but this 2 stands for the secondary winding. Now this 2 stands for the loading conditions, or this 2 stands for I2 current, because if there is no load, then there is no I2, there is no magnetomotive force, then there is no flux. But here what it is happening, once the load is connected, secondary current it will be existed. So once the secondary current established in the secondary winding, then there will be a magnetomotive force in the secondary winding. It will supply its own flux, that is nothing but the pi 2. So as per the Lenz's law, what could be the direction of this pi 2? What is the cause for this pi 2? That is nothing but the secondary induced EMF, E2. Now because the cause for pi 2 is nothing but I2. So I2, the cause for is nothing but that is the E2. So always this pi 2, it will be in the opposite direction to the flux. So what could be the direction of this flux means that will be in the opposite direction to the actual flux. That is the main flux is nothing but this is the pi naught, and this load flux means this pi 2. Sometimes it can also be called as the load flux, because that flux is establishing in the magnetic core because of the load only. So this pi 2, it will be in the opposite direction to the main flux or no load flux, that is nothing but the pi 2. So what made to select, what made us to orient this flux in the opposite direction means based on the Lenz's law. As the flux pi 2, oppose the flux pi naught, the resultant flux of the transformer decreases. So here, if you could observe in this particular region, this pi is traveling like this pi naught is traveling like this, and this pi 2 is nothing but it is traveling like this. So both are traveling to each other in the opposite direction. So in this case, whatever the total flux, it can be seen in the magnetic flux. So that may be pi, it is nothing but time to time it goes on decreasing. Once this magnetic flux in the magnetic core goes on decreasing, then the primary induced EMF, even which is also directly proportional to the flux and frequency, anyhow frequency is constant. So once this flux goes on reducing, this induced EMF in the primary winding also reduces. Once this induced EMF in the primary winding reduces, then this I0 current slowly increases. It will becomes I1 current. As why I am writing this I1 current means, this is simply in the simplest words we can write V1 minus E1 to the Z1 is nothing but the I0 current. Whenever this E1 goes on decreasing because of weakening of this flux because of the load, now once this E1 goes on decreasing, then proportionally this I0 current will also increases. This I0 current is also increases, thus that may be towards I1. Because anyhow, this no load current may not be no load current, because anyhow the load is connected. Once the load is connected, I0 no more I0, it becomes I1 current. So I1 current is establishing means, so some additional amount of current will definitely it will flows into the primary winding. Once this additional amount of current it is flowing in the primary winding, proportionally there will be another flux. That flux is nothing but because of the load it is appearing in the primary winding. So that flux is nothing but the pi 2 dash. So how much of weakening of this flux is taking place? How much of weakening of this flux is taking place because of pi 2? Proportional to this, your induced EMF goes on reducing. Proportional to this, your I1 current increases. Proportional to this, our pi 2 dash increasing. So if you could clearly observe the magnitude of the various fluxes, this pi 2 dash and our pi 2 will almost of all same. So, but and whatever the direction of this pi 2 dash and pi 2, as per the Lenz's law, it will be opposite to the cause. So, what is the cause here? The resultant fluxes, the differences in the flux. So, our pi 2 dash and our pi 2 both are traveling to each other and the magnitudes are same. Then pi 2 dash and pi 2 will cancel each other. Then finally, our total flux will becomes pi naught only. So that is the reason in the beginning of the videos only I told you very clearly that always the magnetic flux remains same. Whether you are keeping no load or 100% load or 50% of load, whatever it may be, always that magnetic flux is nothing but it will remain constant. Because if the load changes, proportionally what happens, it will draw excess amount of current, then proportionally there will be opposite flux to the main flux, and proportionally some counter flux it will be supplied with the primary voltage source. That counter flux and opposite flux cancels each other. So finally there will be a primary current balance, primary counterbalancing current, that is nothing but the I2 dash, it will be established. This I2 dash is nothing but, this is because of weakening of the magnetic flux. So finally I1 is nothing but the vector sum of I0 and I2 dash. Now proportional to this I2 dash, there will be a flux, that is nothing but the pi 2 dash. Now it is very clear that I2 dash is nothing but, that is because of the load existing in the primary. So that is the reason this is called as a primary counterbalancing current. So what about the counterbalancing magnetomotive forces in the primary and secondary means? Now in the primary this is N1 into I2 dash. In the secondary that is nothing but N2 into I2. So if you want to calculate I2 dash, that is nothing but N2 by N1 into I2. So this is nothing but I2 dash is nothing but, this is I2 dash. I2 dash is nothing but K into I2. So this I2 dash is nothing but K times of I2. This is nothing but the primary counterbalancing current existing in the primary. Don't confuse with this. I2 dash, it always appears in the primary loop only, not in the secondary. So I2 dash is equal to K times of I2. So this is the phase difference between V1 and I1 gives the power factor angle pi 1, and the power factor of the secondary side depends upon the type of the load connected to the transformer. So finally, what will be the total current in the primary winding is nothing but I1 is equal to I0 plus I2 dash. So I1 is equal to I0 plus I2 dash is nothing but, this will be the total primary current in the primary winding. So this I2 dash is nothing but K times of I2. This is also represented as I0 plus K times of I2. So this I2 is nothing but the load current. So if you want to draw the phasor diagram of the transformer and inductive loads. So if you want to draw the phasor diagram, first of all we should know what about the voltage balance equation. Let us write the voltage balance equation in the primary secondary winding, that is V2 plus I2 into Z2. So this is V2 is a phasor and this is I2 into R2 plus J times of X2. So this is furtherly it can be simplified as V2 plus I2 R2. This is one loop plus J times of I2 into X2. So this is nothing but the reactance loop. So this total value is nothing but it becomes E2. So let us start with the basics here. First of all, always this reference axis must be a flux pi, because just now also we have discussed that flux always remains constant. And with respect to V1, now let us say this is V1 only. Don't go for V1 dash initially. This is V1, and between V1 to I0, this is the one case. This is nothing but the pi naught. Let us start with the basics. Between V1 to I0, that no load power factor angle will be there. And this I0 can be resolved into two perpendicular components. Just how we have completed these points as part of our phasor diagrams for no load conditions. Now that is a procedure to draw the IW and MU. Now here, now if you are representing all these things, it becomes so much of complex. So that's why I am eliminating for our simplification the no load circuit components like IW, MU, R0, X0 for a while. And this is I0 component, just orbitally you can draw it here. And next, with the help of this V1 and I0, now let us proceed to the loading characteristics. What are the loads here? Now let us assume that load is nothing but the inductive load. If it is inductive load, now this becomes your pi 2. This is nothing but this is V2 is nothing but orbitally we have taken one vector here. Now this is V2 axis, and next one is if V2 is this one, then I2 becomes just above this, because it is the power factor is nothing but the lagging power factor. So this is nothing but the I2 quantity. Just you draw the V2 here and just draw the I2 here. Now If you want to draw E2, secondary induced EMF, E2 is equal to V2 plus I2R2. So to V2, to this particular component or to this particular V2 vector, we had to draw I2R2. So what is this I2R2? I2R2 is nothing but, how can we add this I2R2 vector to the V2 means, I2R2 is always in the direction to the I2 current. So what is the I2 current here? Now this is the I2 current. So in the same direction, in parallel to this I2, let us draw a vector with a magnitude of I2R2 in parallel. So in parallel to the I2. So and this vector I2R2 must and should start from the terminating point of V2. So where this V2 is terminating here, this is the point where V2 is terminating. From this V2, in parallel to this I2, let us draw a vector, and what could be the length of this vector means that length is nothing but the I2R2. So now this is the V2 plus I2R2 is nothing but this is the vector. Then after that, for this I2x2 by j times. So j operator means for this vector, once if the j operator is applied, then automatically the resultant will be rotated by 90 degrees. So this is the rotation, otherwise it will be continue like this. Now once if it is added, then this becomes 90 degrees, it will be revolved by 90 degrees in an anti-clockwise direction. So that's why this becomes I2x2. So this I2x2, what could be the length of this one means, the length is nothing but I2x2 is the length, and angle is nothing but it is anti-clockwise direction by 90 degrees. So now this vector, if you could measure here, this is 0, this is V2, then I2R2, this is 0, from here to here, this is V2, then from V2 to here, I2R2, and if it is continue like this, but it is rotated by how many degrees? 90 degrees, because j operator is there. So this is I2x2. So V2, I2R2 plus j times of I2x2. V2 plus I2R2 plus j times of I2x2. This is the vector. So if you are joining all these three together, so finally we are going to get the E2. So if you are extending from the starting to last point, that becomes your E2. So this is the method we are going to follow to compute the phasor diagrams under load cases. Suppose instead of inductive load, if you are taking resistive type of load means now I2R2, V2 and I2 are in the same direction. So from the terminating point of V2, let us draw a continuous vector, and then again a I2x2. Only here only it will be changed based on the power factor angle. And coming to the primary winding, what is the procedure? Now here for the primary winding, the voltage balance equation is V1. This is a minus E1 because both are opposite to each other. So this is I1 into Z1. So if you want to simplify this, minus E1 plus I1 R1 plus J times of I1 X1. So let us assume V1 here. Now let us assume this is nothing but the V1. So for a while you please ignore this V1 dash. Let us assume this is nothing but the V1 only. From this V1 is nothing but how it will be computed. So this will be computed now, or otherwise you can say this as this is a E1 vector. Now if this is the E1 vector, not exactly the magnitude, this may be somewhere here. This may be E1. So how can we compute this V1 vector? That is the vector sum of minus E1 plus I1 R1 plus J times of I1 X1. So minus E1 means you have to extend this E1 vector by 180 degrees in the opposite direction. This may be, so instead of this may be written as minus E1. For this minus E1, we have to draw I1 R1. So first of all, you should know the direction of this I1 vector. What is this direction of I1 vector? So we know that I1 is nothing but I0 plus I2 dash. So vector sum of I0 plus I2 dash. So already we know the I0 direction. I2 dash we should know. Whatever the direction of this I2 dash, it will be extended by 180 degrees with respect to I2 vector. So already we know I2 vector. Now this is the I2 vector here. This is the I2 vector. So you extend this line in the opposite direction. So if you are extending this line in the opposite direction, you will get the I2 dash here. Now this line and this line is in the quite opposite direction. This is I2 dash. For better understanding, I have given, in order to give some space here, I have tilted this rectangular in little bit upward direction. Otherwise, this I2 vector, and this I2 dash vector must be in the opposite direction. So let us assume this is I2 dash, and after getting this I2 dash, and anyhow we know I0, let us take the resultant of this. So that current is nothing but the I1 current. So the I1 current is nothing but I0 plus I2 dash. I2 dash is nothing but it is by 180 degrees with respect to the I2. Already we know the I2 vector. We have arbitrarily chosen some vector for I2 because this was selected based on the loading condition. What the type of load it is. So this is I2 in the opposite direction to the I2. I2 dash will be there. I2 dash and I0. If you are constructing a, so what will be the resultant value? So the resultant value is nothing but the I1. So now coming to this algebraic vector equation, minus E1 plus I1 R1. So I1 R1, it has to begin at the terminating point of minus E1. So let us assume this is nothing but the terminating point. From here, I1 R1 should be drawn. Now this side, this vector and this vector should be in parallel to each other, because in the I1 R1, R1 has no dimensions, only it will be in the direction of I1 vector. So I1 means this is the vector side. So in parallel to this, let us draw a vector with a length of I1 R1. Then again I1 R1 plus j times of I1 X1. So j times of I1 X1 means you have to rotate in the anti-clockwise direction by 90 degrees. So with a length of I1 X1, now let us draw a vector here. So finally minus E1 plus I1 R1 plus j times of I1 X1, this becomes V1. So this is the phasor diagram under loading condition if the load is nothing but the inductive type load is there. So clearly I have given the various steps to be followed to construct the phasor diagrams. So these are the various steps. And next, similarly, we can draw the phasor diagrams of transformer for capacitive type of load. This is the capacitive load and this is nothing but the resistive type of loads. Now here also, just now also I have explained, this is nothing but the V2 vector and I2 R2 in the same direction because resistive type of load. In the leading case, what happens if this is a V2, this is nothing but the leading power factor. You need not tilt this much, but you can draw here also, no problem. This could be the I2 vector. Anyhow, you at least finally you have to maintain the power factor must be the leading in the nature. So that steps, you need not tilt the vector into the fourth coordinate. Only in the third coordinate itself you can draw the vector for I2 in case of capacitive loads or in the leading power factor case. So this is for resistive load and this first one is for the capacitive loads. And there are various losses. Just now we have discussed copper losses. Copper losses will occur in the primary winding as well as in the secondary winding. And if the proper copper loss is calculated separately in the primary and secondary with the help of equivalent circuits, you can shift the contributed parameters for the copper losses from secondary to primary or primary to the secondary. And next one is the core losses in the transformer. There are two types of core losses. These losses are also called as the magnetic losses. Those losses are nothing but the eddy current losses and hysteresis losses. Thank you for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.